A new system and method has been introduced during the construction of BBT Wolf 2 Shutter Stalin Tunnel at the Podestradal Valley. The basic workflow is to determine and classify geologic characteristics after each blasting, by scanning at the same time the excavated ground with the use of handheld camera or laser scanner. Here is an example of successful prediction of a faulted zone on the lower left part. This faulted zone was predicted before 3 blasts. A successful prediction of the upcoming geology in combination with the damage that can be caused, provides a useful tool in order to reduce costs and risks on excavations. Thus excavation profile can be smoother. The system uses learning algorithms in order to calculate and determine the effect of damage influenced by each parametric blast hole and corresponding rock type. Hence a third nonlinear statistical model that is constituted by virtual x, y, z points, represents each upcoming damage based on the finite geologic and topographical survey of excavations. Predicted model is being used for linear definition per blast hole, and thus calculation of the suitable blast hole's position or explosives weight can be accurately established. An overbreak-underbreak of predicted nonlinear map and linear section was eventually delivered for each blasting round, and targeted adjustments took place. Had been used as a reference the predicted damage on the influenced range for each blast hole. Thus the suitable drilling offset position was extracted as an actionable plan for the contractor. A prediction of forthcoming over-under-break damage were taking place on daily process of excavations. A combination of geological or non-geological factors used on the appropriate time frame demand. Point cloud of each excavation were recalled from database and probability models were calculated. The location and elevation of upcoming overbreak damage were being produced statistically. Based on the predicted situation, targeted adjustments were defined regarding the parametric offset of drilling stakeout. Has been used as a reference the theoretical excavation line or the lattice girder that is usually placed on its theoretical position. In addition, the third graph were finally produced, presenting the predicted damage per blast hole in a linear or nonlinear analysis. An automate process of 3D color maps can be received with mobile third video sensors and point cloud generation. A new edition of the basic workflow may be added and integrated into a combined system providing live geologic documentation. The system may also include wireless transferring of information received from tunnel to office and office to tunnel for live prognosis based on the results found. The 3D sensors can even replace photo scans and proceed with the overall process as mentioned before. Operator may proceed more easily and draw on touch screen faulted zones or joints based on contour lines and tunnel face color mapping.
Drilling hardness is estimated and categorized in accordance to the rock mass class. Before each drill and blast event, it is critical to determine the effect of blasting on the tunnel surface. Until now, overbreaks and underbreaks estimation is done based on experience. This technology transforms the georeferenced point cloud into projection of the actual excavation. With this projection method can be determined the hardness. This technology interpolates point cloud of each drill and blast excavation. This kind of interpolation has direct effect on underbreak and underbreak mapping, as well as the primary scanning area. Interpolation calculates and defines the damage per drilling hole in gridded squares. Each square describes the average damage. Each square is positioned in relation to the direction of each drilling. In the particular example, the interpolation resolution is calculated so as for each drilling to be represented of 5 squares. Each of the 5 squares per drilling has the same affecting area but different elevation that describes the average overbreak and underbreak damage on the specific direction of excavation. In the particular example, the 5 different colors represents the overbreak damage of each area in the total length of the specific drilling. Furthermore, as this example is represented the interpolation effect in relation to the actual scanning. Each square is described by a single point coming from the point cloud average. The same methodology described until now is used for all drill and blast excavations. On the next step, it will be define the hardness of a future excavation. The interpolated excavations of the past are recalled from database and are ready to be used. Each drilling hardness that belongs to the same position with the future excavation is separated from the database coming from the past excavations. Now we are going to recall the squares of a specific drilling position of past excavations that has also the same hardness with our future excavation. It will also be shown how damaged squares of the past excavations were calculated. It is obvious that each drilling is in the middle of the squares that is represented. This describes the effect of damage caused from each drilling and each square region that is constituted. For each square of the specific drillings of the past excavations that also matches with a position and hardness of the future excavation, is calculated the average overbreaks and underbreaks damage. This calculation comes from the point cloud included in each determined square region. For the particular example, from each past excavation is calculated the first, second, third, fourth, and fifth square that belongs to the specific position and hardness with the future excavation. Since this determination is automatically done, the calculation procedure acts immediately. By recalling the average damage of each square of the past excavations, then the forecasting of overbreaks and underbreaks is mapped to the position of future excavation. Excavation forecasting defines a logical model of a future excavation based on the parameters of drilling hole's position and hardness defined. Each predicted square has a single point of overbreak and underbreak damage that comes from the average of past excavations. Now it will be presented the example of a forecasting surface calculation, defined by the drilling position and hardness of the past excavations. The average of past squares will be calculated to the specific position where same hardness with them has been defined on the future excavation when drilling is done.
Excavations during tunneling construction are not possible to approach the absolute theoretical surface. The main reason is the unexpected ground soil situations that can be found during infrastructure. Each excavation is dependent on personal or engineer's experience. There is a limitation of accurate decisions that would help to approach the best excavation result. This example represents the point cloud surface of an actual excavation. In order to estimate the future surface behavior so as to prevent critical excavation issues, different opinions may come from different people. The main reason behind those discrepancies is that there is not a realistic excavation forecasting based from previous point cloud measures. In addition, overbreak or underbreak areas that may cause from a bad excavation prediction increases dramatically the cost of construction. Generally, the excavation behavior for each particular soil is an unsolved issue that concerns many tunnel engineers. For every 10 centimeters of overbreaks may increase the excavation cost to more than €1 million per kilometer. The domino effect that may come from bad excavation prediction follows the project until the end. Tunnel excavation forecasting provides sophisticated mathematical algorithms and a self-teaching process that learns from previous measures. Namely, the point clouds of each excavation are grouped according to each soil type. What you see now is the creation of virtual point clouds that represents the excavation forecasting estimation of the different soil types that exists more front where the actual excavation is. In the particular example, you can see the forecasting calculation of 4 future excavations. In addition, the forecasting virtual point clouds are transformed into developed mapping. Thus, engineers will have the opportunity to inspect excavation forecastings from the plane view. Forecasting surface deformations are easily readable from the plane view, offering thus to engineers a priceless tool in order to predict and prevent excavation risks. Engineers can select several forecasting parameters. In accordance to the selection, point cloud forecasting is changing. This invention removes the obstacles between different opinions by adapting common basis forecasting informations where decisions can be taken instantly and at the same time more reliable and precise. The combination of the virtual point cloud forecasting and the reliable informations that can be provided helps engineers that come from different specializations such as geotechnical engineering, survey engineering, to work efficiently together in a common base and common decisions. Welcome to the future and the revolution of point clouds forecasting. Unfortunately, excavations never reach the perfect theoretical cylindrical tunnel round. Thus, significant overbreaks or underbreaks are created. In the particular example, the edge of the green line represents the perfect excavation, and the edge of the blue line represents the actual situation. As soon as point cloud forecasting is done, then explosives coordination system will calculate the recommended explosive quantities per drilling hole so as to prevent future overbreaks. Thus, the first step is to forecast an excavation that belongs to a particular soil. The second step is to define the possible overbreaks that will exist. The third step is to define the recommended explosive quantities per drilling hole so as to prevent overbreaks before are done. The fourth step is to update the forecasted surface, and thus engineers will have the opportunity to inspect the surface deformation that will be realized from the explosives adjustments to the particular areas. The scope is to reach the green line, which is the best possible result for our excavation. Excavation will become smoother, avoiding at the same time additional costly fill of concrete that would be caused from overbreaks. Now we are going to see the effect of surface that will be realized to the fourth forecasted excavation. Explosives coordination system will update the fourth forecasted surface. Update will estimate of how excavation surface could seem from potential explosives reduction. Namely, the particular mathematical process updates forecasting point clouds via the changes of explosives.